Welcome back. We are about to start Chapter 11. This is Unit 7 in Math with Business Applications. I am Amy Fuchsteiner, your instructor for this course, and we're about to learn about compounded interest. So we're going to be looking at Chapter 11 from your textbook. Compound interest, we're going to be doing future value and present value. Today, we're going to start with Section 1, which is the time value of money. Our goals for this afternoon are as follows. We're going to work through a manual calculation of compounded interest in order to help you understand the difference between the simple interest that we have been doing and the compounded interest that we're going to be doing. We're going to use what's known as the future value table. You will find a copy of this future value table on Blackboard in this week's assignments. If you don't find one, reach out to me and we'll make sure to get you a copy. We're going to have to calculate the interest rate per period as well as the total number of compounding periods, and then we'll use a table factor in order to calculate our compounded amount. From there, I'm going to ask you to separate the interest from the principal. Can you tell which is the interest and which is the principal? We're going to learn how to calculate a table factor beyond the table that you have for usage. We're also going to talk about the annual percentage yield. We're going to be able to calculate it, and we want you to be able to understand what it is and who uses it. Lastly, we're going to use the compound interest formula, which is available to you at all times, even when the tables are not. We're going to go over the different parts of the formula. We want you to be able to identify those, and we're going to be using a calculator with power keys in order to determine the compounded amount. And of course, we'll want you to be able to separate interest from the principal when using the compounded formula as well. So to begin with, the time value of money is a phrase that refers to the idea that money collected today in the present has the potential to be so much more in the future. So money has a value that's dependent upon allowing it time. Putting this a slightly different way, if I have the option of giving you $10,000 today or $10,000 in, say, 5 years, which one would you take today? It's the same amount of money. I'll just give you $10,000 today, $10,000 now, or I'll ask you to wait 5 years and you'll get the same amount of $10,000. Most of the time, we will take the money today because money that we are able to invest today will be worth more money in the future. This is known as the time value of money. So the time value of money is based upon compounded interest. We have 4 ideas here. If you look at somebody who's in retirement or a simple savings account, perhaps they're paying off a mortgage or a credit card. All of these things have in common that they are calculated using compounded interest. This is, we're adding interest onto an account at regular intervals, which we call periods. And we have the opportunity to earn interest on that interest. And if we've borrowed money, then we get the opportunity to pay interest on interest. That's why it's compounded. It just gets more and more complicated as things go on. So there are some terms that we need you to be aware of as we do compounded interest. The first is the idea of present value. This is the money we have now. In the here and now, the money is worth what we say it is worth. $10,000 is worth $10,000. That is its present value. The future value is the money that we will have once the compounded interest is included. So the future value of the money depends upon how we're able to invest it, for how long, at what rate, and how often it is compounded. The time value of money we just talked about. That is that all money and assets can be considered to have both a present value, which is face, and a future value. The opportunity cost is another phrase that you will hear get sort of bandied about a bit, tossed around. This is the idea that there is a change in the future value of money depending upon the decision you make. That means if I decide to put it in a CD versus a savings account versus the stock market, there is an opportunity with each one of those and an opportunity cost. And that sometimes even the decision to do nothing could cost me money or could gain me money. This is known as the opportunity cost. As we calculate some of these ideas, as we calculate some of these values, there we go, we need to have some information. So let's be clear. The principal is the same as it was before. It is the amount of money that is borrowed or invested. The interest rate, same as before. It is going to be listed yearly. In other words, we'll know it's 8% interest for the course of the year or 3% interest for the course of the year. This is known as the nominal or yearly interest rate. However, because we're compounding, that means that at regular intervals called periods, we will need to know what that interest rate is broken down into those periods. We're going to look at the compounded periods, which, as we said, are stated over the course of a year, but we're going to calculate them over the time of the loan. So we'll need to know both things. How many periods are there in a year, and then how many times over the course of the loan. The time in this case, as it was with simple interest, will be given to us in years. Now, I have a graphic on this page that goes over the different compounding periods. So the different compounding periods that we're going to look at are first annually or yearly. This one makes the most sense. It means that there is one compounding period for each year that you have the loan. The second compounding period is known as semi-annually. There we go. Here it comes. Semi-annually means we're compounding twice in a year, every 6 months. Those are our regular intervals. So there are 2 compounding periods in a year. Quarterly is what it sounds like. Quarters are 4, so there are 4 compounding periods in the year. Monthly, there are 12. Daily, we say 365. There is no ordinary interest when we're dealing with compound. It is always exactly 365 days. There is also something known as continuous compounding. Now, continuous compounding requires a depth of mathematics that is not needed for this course. We need logarithms and exponentials for continuously compounding interest. So if you've had, say, a pre-calc course, you've probably dealt with some of this. We're not going to be dealing with it in this class. So let's try one problem that we're going to do manually. So Charlie places $1,500 in an account that earns 4% interest. We're going to compound it semi-annually. That's 2 times a year. We want to manually calculate the compounded interest over 2 years. So what happens is every 6 months, because it's twice a year, so 2 times a year at regular intervals, every 6 months, we're going to calculate what the interest is, and we're going to put it into the account and add it to the principal. So in the first 6 months, we're going to look at just interest as principal times rate times time. Our principal is the $1,500, our rate is 4%, and our time is the first 6 out of 12 months. This is $30. So those $30 are then going to be dumped into the account or placed into the account. So our new value or maturity value of the account is the $1,500 plus 30, or $1,530. Now, that means when the second 6 months starts, we're actually going to be calculating interest on the new principal of $1,530. That's 4% for the next 6 months. That gives us interest of $30.60. Notice the interest increased just ever so slightly, right? So now we're going to take that interest and we're going to add it to the $15.30 that was already in the principal. That gives us $15.60.60. That becomes our new principal for the next 6 months. So when we calculate interest on this one, we're going to be using the $15.60.60 at 4% for another 6 months, which gives us interest of $31.21. Again, slightly more than it was the last 6 months. This gives us a new maturity value of $1,591.81. During our last 6 months, we'll use that $1,591.81 as our principal. We'll use that at 4% interest for the remaining 6 months, which gives us $31.84. Again, slightly more than the last bit of interest. This gives us a maturity value of $1,625.65. So when we compounded the interest, we got a maturity value of $1,625.65. If we had just done simple interest the entire time, so if we had just done the maturity value at simple interest, we would have had the principal, which was the original $1,500 times 1 plus RT, or 0.04 times 2 years, $1,620. That one skipped the line there. So we'd have simple interest would have been $1,620. Do you see the difference? The difference between compounded interest and simple interest. The compounded interest was slightly more, $5.65 more. Not a lot, but just a little bit. Compounded interest will always be more than simple interest. When you look at a chart comparing the growth, you see here in the green what happens with compounded interest. You see in the red a simple interest formula. Notice how the red is a very steady increase. It stays the same versus the green, which starts the same but then sort of shoots up like that. That's known as a compounded growth. The simple interest just stays steady. And of course, the principal, if we hadn't invested it at all, would have just stayed the same, and that's the blue line. In the very beginning, the difference between simple interest and compounded interest is basically pocket change. There's really not a whole lot of difference in those first 4-ish years between those two amounts. It's not until we give time is what makes all the difference between compounded and simple interest. So the next section is section 11.2, and in 11.2 we are going to be using the tables, table 11.1 if you are in your textbook, or the future value table if you are looking at the printout that I offered. All right, so this is a copy of the future value table. You will see that across the top we have percentages, and down the side we have 25 periods. Then halfway through we start with more percentages, 9, 10, 11, and 12, and another 25 periods. We're going to use the future value table in order to help us calculate compounded amounts. In order to use the future value table, we need to be able to identify 3 different things. The first is the interest rate per period. This is your stated or yearly rate divided by the number of compounding periods in a single year. This is known as a lowercase I, and the formula for it, or the description of how to find it, is to take the nominal or yearly rate and divide it by the number of compounding periods in a single year. That's how you find I, or the interest rate per period. The second thing you have to be able to find is the total number of compounding periods. Now, in order to find the total number of compounding periods, you need to know how many compounding periods are in 1 year and multiply that by the number of years that you have to compound. So the number of compounding periods in 1 year times the number of years in the investment or loan. Lastly, you have to be able to find the compounded amount. This is the principal. this is the principal, sorry, multiplied by the table factor. So the compounded amount, also sometimes called the future value or the goal amount, should be the principal times the future value table factor. All right, let's see how this goes. Sometimes these take a while as I'm tabbing through them. So we'll just talk to you for a minute. There we go. So how do you use this future value table? Here is a snapshot of one of them. Basically, what we're going to do is we're going to look at, I believe it's 3% for 18 periods. We want to scan across the top row, looking for the 3% interest rate per period. So if we're going to do 3%, we're going to scan across the top row and find that 3%. Then we want to look at the total number of periods, which is down that very first column, and I believe I do 18 here. We're going to find their cross section. So where does the 3% cross the 18 periods? And we're going to use that as our table factor. We're then going to multiply that table factor by our principal. So there we're scanning the 3%, yep, and then we're scanning across for the 18. You will see that those two intersect at 1.70243, and that becomes our table factor. All right. Now, to find the compounded amount, we will multiply this table factor by whatever the principal is. Let's try a problem and see if we can get it. So dumb. Invested $11,000 at 14% interest, compounded semi-annually for 6 years. We need to find 2 pieces of information in order to be able to use the table. If you don't have your table out, you might want to bookmark it or print it out. I'll wait a second. Okay, so if you've got that now, let's continue on. We've got to find the interest rate per period. So I, or the interest rate per period, is the annual interest rate divided by the number of compounds in a year. This is a 14% interest rate and semi-annually, which gives us 2 compounds in a year. So we're looking for 7%. So we're going to go across the top of that table and find 7%. Then we need to find the number of compounding periods. The number of compounding periods tells us the row we're looking for. N would be the number of compounding periods in 1 year times the number of years. So since it's semi-annually, that tells us 2 compounding periods a year, and we have 6 years here, so we're looking for 12. Our table factor will then be, the future value table factor will be in the 7% column in the 12 periods row, and that should be 2.25219. 2.25219. That should be our table factor. Then to find the compounded amount, we're going to multiply that future value table factor by our principal. So we're going to take 2.25219 and multiply that by $11,000 to get 24774.09, or $24,774.09. So what does that mean? That means that if he put in $11,000 at 14% interest and let it compound semi-annually for 6 years, there would be 12 times that they put interest into the account. And each of those 12 times, interest would be a little bit higher than the last. The interest that he gains would be a little bit higher than the last, until at the end of those 12 compounding periods, there would be $24,774.09. He started with $11,000, and he gets $24,774.09. He's doubled his money. How much of that would be interest? Well, the interest can be found if we take the compounded amount, the capital letter A, and subtract from it the principal. Since our compounded amount was the $24,774.09, and we subtract the $11,000, this gives us $13,774.09. So yeah, he made a lot of interest. Now, I would just like to point out that no bank gives you 14% interest. No bank, ain't gonna happen. Even CDs or money markets aren't gonna give you 14% interest. 14% interest is a really good stint in the stock market. And I mean really good, because that usually even taps out at, I believe, somewhere around 7 or 8% long term. So while this is a nice exercise, it is not at all reality. Not at all. All right, second example. Oh, sorry, this is not an example. I forgot about this slide. This slide is a practice slide. So much like some of the other attempts, I'll go through a couple of them with you. What we have here is I'm giving you principal and the nominal rate, compounding how many years, and I'm asking you to find the rate per period, the total number of compounds, the compound amount, and the interest earned. So looking at the first column, it's important to note that if it's compounded quarterly, that means 4 times a year. So our interest rate per period would be the 12% interest divided by 4. This is 3%. So each period has a 3% interest rate. The total number of compounds would mean taking the 4 compounds per year and multiplying it by the time of the loan, or 3.5 years. This is 14. On my future value table, table 11/1, I am going to look up 3%. That's the column I want. And the row I want is 14 periods. So I'm going to go down the 3% column and across the 14 row. And I'm going to find a table factor in the future of 1.51259. That needs to be multiplied by the principal of 3,500 to get a compounded amount, of $5,294.07. Our interest then would be the difference between the principal and the compounded amount, or $5,294.07 minus the $35,000, for $1,794.07. The remaining 3 problems or examples here, I am just going to click through as I have before. All right, and then we begin with 11.3. 11.3 is kind of a hidden skill. You might want to pay close attention here. This is how to create a new table factor using compound interest. So you might have noticed on this particular table, a couple of things. First of all, that the percentages, aside from the 1/2, 1, and 1 1/2, are all whole numbers. That doesn't happen in the real world, but we'll deal with that in the next section. The other thing is that there's only 25 periods. So that also does not happen. I mean, if you think about just a mortgage, which is generally compounded monthly for anywhere from 15 to 30 years, that's could be as many as 360 periods. This table does not have 360 periods in it. So we need a way to create new table factors using the compounded interest. It's actually fairly simple, so let's get into that. If the total number of periods is not on your chart, there are 2 options. If you have an even number of periods, we're going to have you find half that number. If the number of periods is odd, find the 2 numbers that sum to that total number of periods. The standard procedure for this textbook is to find the 2 numbers that are closest to each other. So for example, even though this number is on the chart, if you were given a number like 20, that's even, so you would split that into 10 and 10. If you were given 21, you would split that into 10 and 11 because those 2 numbers are closest to each other. If you were given 58, you would split that, that's an even number, into 29 and 29. And if you were given 55, ideally they would have you split that into 27 and 28 because they are just one away from each other. Now, that being said, and this is for the adventurous of this set, you could also split 55 into 20 and 25. The problem is that sometimes if you go off script and just pick two numbers that add to that odd one, your digit will be slightly off. The last digit or two will be slightly off. So be careful if you're going off script and just make sure I know which two numbers you picked. Okay? All right. You're going to find the table factor of each of those numbers. If they're even numbers, it'll be the same, because you'll be looking up 3% interest for 20 and 3% interest of 20. And if you've got an odd number of periods, then they'll be different numbers. So there you have to look up two separate table factors. Once you have a table factor for each piece, you want to multiply those two together, so you will have the new table factor. We would then round that to five decimal places. We'll keep a lot of decimals. Yep. I have an example of that one next. And here it comes. All right, so Mark Steele invests $42,000 at 2% interest compounded quarterly for 7 years. Same basic steps apply. We're going to have to find the I and we're going to have to find the N. So the interest rate per period, that's your I, is going to be the annual interest rate divided by the number of compounds per year. This is a 2% interest rate compounded quarterly, so 4 per year. This reduces to 1/2 or 0.5%. 1/2 is on the table, so we can use that. The total number of compounding periods is N. That's the number of compounding periods in 1 year times the number of years of the loan. So this would be 4 times 7 or 28. Now, in the table that I've given you, we don't go up to 28 periods. It only goes up to 25. So I have to create a new table factor for this. 28 is an even number. So I'm going to split that in half, and half of 28 is 14. So I'm going to look up 1/2% for 14 periods. And that leaves me another 14 periods at 1/2%, right? The first 14 periods, there's 28 periods total. The first 14 I'm going to look up first. That's a table factor of 1.07232. And then I'm going to multiply that by the second 14 periods, which is 1.07232. This gives me a new table factor of 1.14987. That's my brand new table factor. If I have to calculate the compounded amount, I'm going to take the future value table factor that I just found and multiply that by 42,000. So I'm going to take 1.1987 multiplied by 42,000 to get $48,294.54. I have another table with more practice. So again, have your table factors ready. Let's run through the first one, and then I'll simply click through the rest. You can jump ahead if you like. So I've got a 16% rate that's compounding quarterly for 10 years. I'm asking you to find the rate per period, the total number of compounds. Show me each one of your table factors, and then give me the new table factor. So at 16% compounded quarterly, quarterly means we're compounding 4 times in a year. So my interest rate per period would be that 16% divided by 4. This is 4%. That tells me what number I'm looking at or which column I'm looking for on the table. Then I need to know the total number of compounding periods. Well, there's 4 per year for 10 years. This is 40 periods. As you look down the first column, you will see it does not go up to 40 periods. So instead, since this is an even number, I'm going to take half of that. For my first table factor, I'm going to look up 4% for 20 periods. And then I'm going to look up 4% for the remaining 20 periods. This is 2.19112 times the 2.19112. This gives me a new table factor of 4.80101. Looking at the second example, we see we have 6% compounded monthly for 4 years. So monthly compounds gives us 12. Our interest rate per period then would be the 6 divided by 12. There we go. 6 divided by 12 is 0.5%. That is on our table. Total number of compounds would be 48. It's an even number, so we're going to go ahead and split that in half and look up 12% or 0.5% for 24 periods, not once but twice. And when we look at our table, we see that's 1.12716 multiplied by 1.12716, giving us 1.27050 as our new table factor. With the 10%, that's being compounded semi-annually. That's only 2 times a year. So that's a 5% interest rate per period. Our 2 twice a year for 18.5 years gives us a total of 37 compounds. This is our first odd one. So I wanted to make sure to do this one because it is odd. Our table factors that we're looking up then are the 5%, and we want to split up 37 into 2 close numbers. So that would be 5% at 18 periods and 5% at 19 periods. Notice I have listed these out. Could you have used 20 and 17? Absolutely. Ideally, we want to keep them just one number apart, but yes, you could have used 20 and 17, and that would have worked as well. Looking up 5% for 18 periods, we get 2.40662, and 5% for 19 periods gets us 2.52695. Multiplying those two together, you should get 6.08141, and yes, I am blocking that number. For the last one, I'm just going to go ahead and click through here. It is only annually, so the 7% stays the same. 45 years breaks down into 22 and 23, and you should have a final table factor of 21.00289. Section 11.4 is annual percent yield, or APY. APY is the real rate of return on an investment. It is calculated by taking the interest for a single year and dividing it by the principal. It is worth noting that the more compounding periods you have, the actual higher interest rate you're dealing with. Annual percentage yield takes 1 year's interest, just one. It's always 1 year, and divides it by the principal amount of the loan. The APY will always be higher than the stated yearly or nominal rate. It is why APY is a required statement. It's very much like effective interest rate. It's a required statement on anything that uses compounded interest. As we go through the next couple of examples, I'm going to ask you to compare the APY to the actual table factor. There is a pattern here, and I want to see if you notice it, because if you can notice the pattern, you can shortcut the amount of work it takes here to get to the APY. Let's see if you can find it. Sam invested $4,000 for 6 years at 10% semi-annually. We want you to determine the APY. So the APY is the interest for 1 year divided by the principal, which means I need to find the interest for 1 year. So I've got to go ahead and do a compounded interest problem as if it is for a single year. So the interest rate per period is going to be the 10% divided by 2 because it's semi-annually. So I'm looking for an interest rate per period of 5%. The total number of compounding periods, in the loan it would be 2 times 6, but for APY I just need the interest, the compounding periods for 1 year. So my N here is going to be 2 times 1. I'm going to look up a table factor for 5% and 2 compounding periods. This gives me a table factor of 1.10250. 1.10250. Our compounded amount or our interest for that single year would then be the 1.10250 times the $4,000 in principal, or $44,410. Our interest then for that year would be the $4,410 minus $4,000 in principal, or $410. Now I finally can do the APY because I can take the interest for that single year, the $410, and divide it by the $4,000 that was the principal. So $410 divided by 4,000 gets me 0.10250, or 10.25%. Notice that the APY, 10.25%, is higher than the stated nominal. I was trying to say nominal and annual and yearly all at the same time because they mean the same. That 10.25% is higher than the stated interest rate of 10%. That's what APY is supposed to be. You're supposed to get a percentage that's higher than the stated percentage in the problem. But let's compare. Take a minute and compare your table factor, the 1.10250, to the APY of 0.10250. Do you notice anything? I'm not going to say it out loud. Let's try a second example. So Carla's going to take out a loan of $36,000 at 6% interest, compounded quarterly for 5 years. We want to determine her annual percentage yield. If I'm going to do the APY, then I need to figure out how much interest there is in 1 year. Even though it says 5 years on the loan, I need to figure out the interest in the first year. So in order to calculate that interest, I need to find the interest per period, which is going to be the 6% divided by 4 periods per year, or 1.5%. That's my interest rate per period. I need to find the total number of compounds, the number of compounds for 1 year, not the total really. I just need the total for 1 year because APY is for 1 year. So the compounding periods for 1 year would be 4 times 1, or 4. So when I look up the table factor, I'm going to look up 1.5%. Yes, that's on the table. 1.5% for 4 compounding periods, and I get a table factor of 1.06136. If you understood the pattern from the last problem, you already know the APY. I'm just saying. But we'll continue on. So to find the compounded amount for 1 year, I'm going to take the future value table, 1.06136, and I'm going to multiply that by the principal of $36,000 to get $38,208.96. I only need the interest, so I'm going to subtract $36,000 from that $38,208.96 to get $2,208.96. I can finally determine the APY by taking the interest from that first year, the $2,208.96, and dividing it by the principal of $36,000. This gets me 0.06136, or 6.136% as the APY. Notice again, the APY is slightly higher than the stated interest rate of 6%. It will always be higher, not always by much, but it should always be higher, all right? If you haven't caught on yet, let me point out again. If you take a look at your table factor, the 1.06136, and you compare that to your APY of 0.06136, you should notice something. If you caught on in the first example, were you right when we got to this one? All right. The last section from 11.1 is the compounded interest formula. This is a somewhat complicated formula. You will need a calculator with an exponent key in order to figure these guys out. Don't think you can necessarily just use your phone calculator or just use your computer calculator unless you know the trick about switching it in order to get your exponents. So the formula for compound interest is as follows. A is equal to P times 1 plus I to the nth power. This is A, as in the total or compounded amount, is equal to P, your principal. That's the amount of the investment or of the loan, times the quantity 1 plus I. This is your interest rate per period. We've been finding it for the last 35 minutes. It is still the same. N is your total number of compounds. It is what we've been finding for the last 35 minutes. You still have to find your I and your N as we did previously. We're now just going to put it into this formula. When do we use the compounded interest formula? 2 occasions, really. As we had said, in real life, your interest rates are not whole numbers. I mean, my car loan was like, I want to say my car loan was 2.3%. My very first home loan was 5.4%. So they don't all come in a table, or the table needs to be like a tome. Tome might not be a word you're used to. A tome is a very large book, right? It could be a very large book. And before we had computers, they were all in very large books. Now you just put it into an Excel spreadsheet and the banker does it for you. But sorry, I digress. All right, let's try a problem. I have my scientific calculator here. This is the one that I normally use. This is the one that I recommend for class. It's just a TI-34. Any calculator with a fraction key and an exponent key will work. All right, so let's take a look here. So here we have calculate the future value of $22,560 if the interest rate is 7.2% compounded monthly for 8 years. So even to use the formula, I still need to find the interest rate per period. The main difference here is that you will do the interest rate, the percent, as a decimal. So when I do I, purposefully to put it into the formula, I'm going to use the annual interest rate as a decimal. That's the main difference. And I'm still going to divide it by the number of compounds in a year. So 7.2% as a decimal would be 2 places to the left, or 0.072. Since it's compounded monthly, I'm going to divide that by 12, and that's going to give me 0.006. So my I value, or interest rate per period, is 0.006. My total number of compounds would be 12 times a year for 8 years, or 96. 96 never would have been on our table. So with those 2 values, and knowing the principal is 22,560, I'm going to substitute them into the compound interest formula. I know A is equal to P times 1 plus my I to the nth power. So this would be 22,560 times 1 plus 0.006 to the 96th power. So 1 plus 0.006, do what's in parentheses first, to the 96th power. This is, well, it's a basic calculation. You have to do the power first. 1.006 to the 96th power. On most calculators, on the TI-30 calculator, what you want is in the first column, and it's about halfway down. It's called a chevron key. I'll hold it up there. See, whoops, go the other direction, Amy. Right here. Looks like a caret or a chevron, right? So we're going to take 1.006 to the 96th power, and we're going to get 22,560 times 1.775849466. You don't want to round this. You do not want to round. The bank will not round. It takes money out of their pocket. Banks will not round. So we are not going to round. We are going to keep all the decimals. Now, if you know how to use your calculator correctly, you know you won't have to clear and retype that. You can just get 1.006 to the 96th power, and you can just multiply that times 22,560 to get $40,063.16. We're rounding to dollars and cents. All right? If, as you do this, you're having problems figuring out your calculator, then you may want to go ahead and schedule an appointment with myself or Tim, where we will help you work through how to get this done. I will also put up a video, but the problem is that not everybody uses the same calculator. So I may not hit all of your issues. You may have to log on with me at some point this week to get it figured out. Here is a second example. Find the amount of an $89,000 loan compounded quarterly at 5.4% over 30 years. This is approximately my first mortgage. So my house cost me about $89,000. That was back in 2002. Some of you were probably just born. And it's compounded quarterly at 5.4% over 30 years. So we're going to do the same steps. I still need to find the interest rate per period. And in order to do that, I'm going to find the annual interest rate as a decimal, and I'm going to divide that by the number of compounds in a year, or 0.054 divided by 4, which is 0.0135. I need to find the total number of compounds. Well, if we're compounding 4 times a year for 30 years, that's going to be 120 compounding periods. I'm going to substitute these values into the formula along with the principal of $89,000. So I'm going to have $89,000 times 1 plus 0.0135 to the 120th power, or 89,000 times 1.0135 to the 120th power. Doing that first exponent, so 1.0135 to the 120th power, I have to do that part first. That gives me 89,000 times 4.998622773. I need to keep the whole number, or $444,877.43. Again, if you're not getting that number, please schedule some time with me. Reach out via email. Ask me to send you a video specific to your calculator. There we go. I just couldn't get those words out. I don't know why. All right, here I have 3 other examples. Determine the future value of $5,000 at 8% interest compounded semi-annually for 18 years. Our I value would be the 8%, 0.08, divided by 2, because we're compounding semi-annually, or 0.04. Total number of compounds would be 2 per year for 18 years, or 36. The formula then would be 5,000 times 1 plus 0.04 to the 36th power. Working this out on the calculator, we get $20,519.66. Second example, the value of $250,000 at 2.4% interest compounded monthly for 6 years. 2.4% interest as a decimal would be 0.024. We're going to divide that by a monthly compound of 12 compounds in 1 year, to get 0.002. Total number of compounds would be the 12 per year for 6 years, or 72. Then substituting these values into the formula along with a principal of $250,000, I get 250 times 1 plus 0.002 to the 72nd power, or $288,679.51. Lastly, we have the future value of $9,000 at 13% interest compounded daily for 3 years. Okay, we're going to get a huge number here because 13%. No, that should be 1.3. That should be 1.3% interest. Hold on. Let me fix that. We're going to put a decimal point there, and then I'm going to fix it later. Pen, decimal point, 1.3% interest. Why? Because nobody gets 13%. Nobody. All right, done. Okay. So then if we fix that up, I don't want a laser pointer either. What's that doing? Okay, then what we're going to have is 0.013, because it's 1.3%, times, or divided by 365, because we're compounding daily. That means every day I earn a little interest, and they dump it into my account, so I can earn a little interest on that interest. Look at the number I get, 0.0000356161. Okay, my end value here, total number of compounds, would be 365 compounds a year for 3 years, or $1,095. Substituting those values into the formula, we'd have 9,000 times 1 plus, and I didn't want to write that whole number in. No, I did not. So I just used 0.013 divided by 365. You can do that. In most calculators, it will work. And if you've taken, an Algebra 2 course and maybe a geometry or pre-calc, you're probably pretty savvy about how to get that done on your calculator. We're going to take that to the 1,095th power. Woo! Ooh, go back. I slapped my keyboard. There we go. And we're going to get $9,357.93. Yikes. Okay. Last slide here with practice on it. If you want to, you can skip over this part. I'm just going to click through. These all use the formula A is equal to P times 1 plus I to the nth power. And I've gone ahead and worked through this. You can check your understanding by doing these problems yourself and then pausing and clicking through this with me. I would say probably the hardest one is the $15,000 for 25 years at 5% compounded daily. That's like the example that we just went through, where it's probably to your benefit to keep the 0.05 divided by 365 rather than typing out all of the numbers. So that would be the only one. All right. That is the last bit of Chapter 11, Section 1. So at this point, do you feel like you could work through a manual calculation of compounded interest to help you with understanding? Do you feel like it helped you? I'm not going to make you do another manual calculation, but do you feel like it helped you? Do you feel like you could use the future value table, including finding the interest per period and the total number of compounding periods? Could you calculate the compounded amount and separate interest from principal? Could you tell me how much was interest and how much was principal? Are you familiar enough to be able to calculate a table factor beyond the table? You will have resources, so while I've talked you through that type of problem, do you feel like you could do so yourself? Could you calculate an APY or an annual percentage yield? Could you use a compound interest formula, including identifying and finding each part of the formula and using a calculator to find the actual compounded interest? And of course, separating that interest from the principal. This is a lot of things in this presentation. Do you feel comfortable doing all of these things? There is extra practice. This is Chapter 11, Section 1. It is at the end of the section in your eText. There are, I believe, 39 review exercises. You could do as many or as few of those as you like. And if you have a physical copy of the textbook, I believe this is pages 350 to 353. Either if it is not, it will still be at the end of Chapter 11, Section 1. There is, of course, a graded assignment that goes along with this presentation. It is located on WebAssign and is oh so creatively titled Chapter 11, Section 1. As always, if you have any concerns or need any assistance, please feel free to contact your instructor, the embedded math support personnel, the Math Center, and any tutors you may have available to you. Thank you so much. We are all here to help.